Lesson 2, Impulse Graphs. In this lesson, we're going to look at force as a function of time graphs and how they relate to impulse and momentum. Remember from the last lesson, the relationship impulse equals change in momentum, where impulse is determined by the formula F delta t, where F is force and delta t, or change in time, is the time interval over which the force is exerted on the object. The change in momentum is delta p is m delta v, mass times the change in velocity that occurs over that same time interval. If we plot a graph of force as a function of time, it tells us useful things about the impulse on the object. If we look at the area under this graph, we get a square-shaped area, and the area of the square, length times width, is force times the area of the time axis that the graph is over, or change in time, and F delta t is impulse. So if we take the area under a force as a function of time graph, we'll get the impulse. When we say under, what we really mean is between the graph and the x-axis. If the graph is below the x-axis, that means that we have a negative area. If it's above the x-axis, we have a positive area. You'll be expected to find a variety of different areas: squares, triangles, combined shapes, and trapezoids. The area of a square is length times width. The area of a triangle is 1/2 base times the height of the triangle, where the base is the distance the triangle extends along the x-axis, and the height is how high it comes up along the y-axis. If you have combined shapes, you could have a series of triangles or squares added together. Watch for negative areas. These occur when the graphs go below the x-axis. Negative areas should be subtracted. For trapezoids, we have combinations of squares and triangles. For the trapezoid in the picture above, we have the area of a triangle plus the area of the square in the middle plus the area of the triangle on the other side. So this would be a combination of shapes. You'll calculate each area separately and add them together. But you'll never be asked to find the area of a curved graph, like this. This is the kind of area that you're going to be finding in calculus, but isn't really easy to find geometrically. Here's an example. There is a force as a function of time graph for a 1,500 kilogram car. The graph is sloped down, but it never goes below the x-axis, so it remains a positive area. The area of the triangle I've shaded blue will tell us the impulse. The area of the triangle is equal to the impulse, and the area equals 1/2 base times height, where the base is 5.78 seconds and the height is 3,012 newtons. So the area will be 1/2 5.78 times 3,012. This gives us an area of 8,704, which means the impulse is 8.7 times 10 to the 3 Newton seconds. What is the change in speed? Well, we know that impulse equals the change in momentum, which is m delta v. So delta v is impulse divided by mass, or 8,704 divided by the mass of the car, which is 1,500 kilograms. So we get a change in velocity equal to 5.80 meters per second. In this example, we have two different graph shapes. We have a triangle in the positive region of the graph and a rectangle in the negative region. Remember, when you have a negative area, it should be subtracted. Impulse is equal to change in momentum, and the impulse is also equal to the area under the curve. So we need to find the area of the triangle and subtract from it the area of the rectangle. The triangle is 1/2 base times height. The rectangle is length times width. The base of the triangle is 5. The height of the triangle goes to 10. The rectangle has 2 squares on the x-axis, so the length of the rectangle is 2. The width goes to -5, or just 5. So the total area is 1/2 5 times 10 minus 2 times 5, which gives us an area equal to 15. So the change in momentum, which is equal to the impulse, is 15 kilogram meters per second.